Hi, I'm Gilman from Worcester Polytechnic Institute, and I'm going to be talking to you today about application concurrency mechanisms on NVIDIA GPUs. So to begin with, what do I mean by concurrency? Well, a common problem in data centers which use GPUs to accelerate deep learning tasks is that there are frequently low utilization periods where resources on the GPU are simply left idle. One solution to this problem has been to run more than one application together when this low utilization occurs. For deep learning tasks specifically, this means running multiple inference or training tasks together on a single GPU. So in this talk, we are going to look at a single question that is posed by concurrent deep learning on GPUs. Are current GPU scheduling mechanisms sufficient to guarantee predictable and low turnaround times while also maintaining high utilization of GPU resources? We first looked at the mechanisms available on NVIDIA GPUs to run applications concurrently. And there are three: priority streams, time slicing, and MPS. And we analyzed their main features. We characterized their performance for a set of deep learning inference and training jobs. In doing so, we found that concurrent execution on GPUs is suboptimal without the ability to reassign resources dynamically, which the current concurrency mechanisms are missing. They additionally lack the ability to sufficiently prioritize the progress of one task over another. Without these two features, it is difficult to maintain both low turnaround times and high utilization at the same time. And finally, we find that fine-grained preemption is a promising solution to these issues we found with predictability and utilization. So let's start with the characterization of the workloads that we looked at. At a high level, we are interested in a specific kind of concurrent deep learning workload. In this case, there is a high-priority inference job, which consists of a series of inference requests from users. For these, we want to service these requests as quickly as possible, as often as possible, with as little variance in predictability as we can achieve. There's also a low priority training job, which is a training task for a single model on the same GPU in order to achieve higher GPU utilization when the inference task isn't making use of all of the resources. Now, a quick overview of how applications are executed on a GPU. Here is a high-level portrayal of a GPU with the two jobs ready to be executed. An application is essentially a sequence of kernels which are launched one after the other, shown here on the left. Each kernel is divided into a grid of thread blocks, each of which are the same size and execute the same code in parallel, independently of each other. These thread blocks are transferred to the GPU and scheduled to its streaming multiprocessors, or SMs. SMs have a fixed set of computational resources like threads, shared memory, and registers that they can assign to thread blocks in order to execute them. So, since we scheduled this A1 kernel to the SMs, let's say we still have some space left over for us to schedule more kernels. We can then go back and take, say, the first kernel from job B and schedule its thread blocks to the SMs too. However, if you recall, kernel A is higher priority, so perhaps we would instead want to schedule the next kernel of job A. In fact, different concurrency mechanisms would make different choices here. This illustrates an important point. Depending on which mechanism is used, you can change where and when thread blocks are scheduled to the GPU. Now, let's get into the specific characteristics of the workload we looked at. We looked at models from two sources: the MLPerf inference and training benchmark suites, and the set of PyTorch example models. For the PyTorch models, the inference job was always a series of 5,000 consecutive inference requests for the same model. For the MLPerf models, we had two modes. The consecutive mode was identical to the PyTorch inference job, while the server mode had requests arrive according to a Poisson distribution. For both, the training task was just a few epochs of training for a single model. These jobs had a few characteristics that are relevant to our analysis. So to start, each one was a sequence of kernels that were executed on the GPU serially. So basically this means that the resource usage for any given job fluctuated over the course of its execution as different kernels were launched, making it difficult to consider its resource requirements holistically. Looking at these kernels, we noticed that the training jobs often had a sizable portion of long-running kernels. This is significant because these kernels occupy the GPU for a long period of time with no way to interrupt them, taking up resources that might have been more useful to give to the inference task, for example. Additionally, both inference and training jobs often had a significant amount of large kernels, which had grid sizes large enough that the entire kernel couldn't fit onto the GPU all at once. This prevents such kernels from being co-located with other kernels from different jobs while they are on the GPU. So now we look at the concurrency mechanisms currently available on NVIDIA GPUs. So we'll start with priority streams. When using priority streams, the kernels of two applications are launched from within the same process on separate CUDA streams. And so CUDA streams are essentially independent sequences of commands that are executed in the order they were issued. So these streams can be assigned one of three priorities ranging from -2 to 0, with -2 being the highest priority. Importantly, it makes use of the scheduling policy called the leftover policy, where the thread block scheduler will always pick blocks from the highest priority stream first when scheduling, and will keep picking blocks from that kernel until there are no more blocks to schedule. It will never pick from a lower priority kernel while there's a higher priority kernel that still has more blocks left, even if it could fit some of the lower priority blocks onto the GPU. However, it will not interrupt any thread blocks currently being executed on the GPU. The higher priority kernel, when it arrives, must wait for any current blocks to finish first before it can be scheduled. So the next one is time slicing. And when two applications are run as separate processes, the CUDA application level scheduler will alternate between the two applications for fixed length time slices, yielding the GPU's computational resources completely to one process for the duration of a time slice. And it schedules these applications in a round-robin fashion, essentially. Only one application's kernels are executing on the GPU during any given time slice, as they are interrupted and switched out at the end of their time slice for the next application to get its turn. However, there is a possibility for an out-of-memory error to occur anyway if the combined resource usage of the applications exceeds the GPU's available resources. Finally, the third mechanism is MPS. Like time slicing, MPS allows applications run as separate processes to execute on a GPU at the same time. An MPS server is responsible for scheduling kernels from each process to the GPU. The major difference from time slicing is that the thread blocks of kernels from separate processes can execute on the GPU at the same time, possibly even sharing an SM. Like priority streams, MPS essentially schedules blocks as if they're from the same context on different streams, but it actually keeps them in separate contexts. However, MPS does not include any notion of task prioritization. Instead, the MPS server can be configured to limit the number of threads that can be used by any one application. MPS is perhaps best suited to cases where the kernels utilize less than the total available resources of the GPU, so basically if they're both small. One of its major features is that the server is able to perform load balancing when there are spare resources in order to spread the work out more evenly across SMs. So here's a summary of the features that each mechanism has. Notably, only priority streams has the ability to prioritize tasks, but it is also the only mechanism that cannot launch applications from separate contexts. Time slicing is also the only mechanism to have preemption, although it is coarse-grained in the sense that the entire application is preempted and removed from the GPU at the end of each time slice to make space for the next application's time slice. Time slicing is also the only mechanism not to allow two applications to execute their kernels on the GPU at the same time. Now we'll discuss our characterization of these three mechanisms on our concurrent deep learning workload. I'm going to go over a subset of the observations we made in the paper due to the time limit, but I'll keep the observation number the same as in the paper, for if you want to look it up later. So first, what metrics are we interested in examining? First, the average turnaround time of the inference requests. We want this to be low, ideally. We also care about the utilization of the GPU. We chose to measure this as the execution time of the training task with the logic that if the idle resources were more frequently being utilized by the training task, as was intended, its execution time would be faster. Finally, we also care about how consistently the inference requests are completed. Observation 1 from the paper. Priority streams cannot preempt executing thread blocks in the middle of execution, resulting in compounded delay and resource contention that led to high and less predictable turnaround times. Here you can see the average turnaround times for the PyTorch models we examined, and you'll notice that the priority streams frequently had comparable average turnaround times to MPS. One reason for this is a phenomenon we term compounded delay. As the priority streams mechanism does not support preemption of executing thread blocks, when an inference kernel arrives at the GPU, it has to wait for the currently executing training blocks to finish. This delay is then compounded each time an inference kernel in the sequence is launched, driving up turnaround times as the higher priority kernel cannot interrupt the lower priority one. However, we also saw issues when the kernels were small enough to fit together on the GPU. Observation 5 from the paper. While MPS increased utilization overall, it also caused intra-SM resource contention that added to the execution times of both the training and inference tasks. Co-location of thread blocks from different applications allows for finer-grained resource assignment, but it can also create contention for resources when the blocks that are sharing an SM require the same resource. The increases in turnaround times compared to the time slicing observed here are partially explained by the presence of this resource contention for these mechanisms where the applications can share the GPU, although MPS is more able to offset this with its ability to load balance. Finally, we come to observation 2 from the paper. Time slicing tended to exhibit predictable and low turnaround times for models with relatively low baseline turnaround times, unless there is memory transfer contention. This came at the cost of poor utilization, as the two tasks never actually executed on the GPU at the same time. So time slicing had extremely low turnaround times for the PyTorch models, and you can see from the variance that it is the most predictable as well. This is largely due to the fact that the two applications don't share the GPU and are thus not able to interfere with each other and cause the unpredictability observed in the other two cases. However, you'll see that the utilization for time slicing tended to be much worse the longer the inference tasks ran for. This is also due to the fact that the two tasks didn't share the GPU at all. The training task is not actually using the spare GPU resources, and is instead forced to wait and execute whenever its time slice comes up, leading to longer training task execution times. However, the inference task execution times for the MLPerf models were much higher for time slicing compared to the PyTorch models we examined. One reason for this occurrence is interference due to memory transfers. These MLPerf models, and particularly the ResNet34 implementation, had a much higher number of memory transfers from the CPU to the GPU than any of the PyTorch models we looked at. You can see here the difference in execution times for kernels of the inference task in red and memory transfer operations in blue. The memory transfer times went up drastically when using time slicing compared to the baseline for this model, while a similar phenomenon was not observed in any of the PyTorch models. This suggests that time slicing is sensitive to memory transfer interference between the tasks, even though the two are technically isolated by not being on the GPU at the same time. Thus, it cannot guarantee low turnaround times for all types of inference tasks. So with these observations in mind, we turn to a potential solution to these issues with fine-grained preemption. And again, we're going to discuss a subset of the observations we discuss in the paper. Essentially, there are two major issues that we want to address. First, the stochastic nature of the inference requests causes both unpredictability and inefficient utilization due to being unable to rearrange or interrupt thread blocks when they are already on the GPU. Second, resource contention also increases the unpredictability even when blocks are co-located on the GPU to improve utilization. There is the potential to improve the performance of these concurrency mechanisms through a scheduling mechanism we term fine-grained preemption. Essentially, this is the ability to interrupt an arbitrary set of thread blocks at any point during the block's execution and relaunch those blocks at a later time. Fine-grained preemption could offer a number of benefits to the existing concurrency mechanisms. For example, it could complement both priority streams and MPS by eliminating the effects of compounded delay for the inference task, since the training task could be interrupted immediately. It could also allow for more fine-grained and dynamic assignment of resources to react to or prevent resource contention, and would give MPS the ability to prioritize tasks in a similar way to priority streams, by letting it interrupt blocks that have already been placed when a higher priority task arrives. It can also improve the predictability of the turnaround times to be more similar to time slicing, but without sacrificing utilization as time slicing has to, by not being able to schedule the two applications to the GPU at the same time. In addition to these benefits, there are a number of opportunities to hide or reduce the cost of fine-grained preemption that are inherent to the deep learning workloads we examined. So this figure shows a subset of kernels from one of the inference tasks we looked at in terms of their execution times. We have time to look at one example here, so let's focus on the region highlighted in red, labeled region B. The first kernel here does not have enough blocks to schedule even one block per SM, so the training task will fill up all of the remaining space, meaning that most of the GPU is currently being used by the training task. The second kernel in region B needs to use up roughly half of the threads per SM in order to fit onto the GPU. To make sure there is already room for this larger second kernel when it arrives, we could preempt enough blocks of the training task during the execution of the first kernel to make that space already available upon the second kernel's arrival. What's important is that the second kernel here only takes 2 microseconds to execute, so on its own, preemption could vastly increase the execution time of the kernel. However, the first kernel takes about 137 microseconds to execute, so it is able to hide the delay that would be incurred if preemption occurs during its execution instead of after, when the second kernel arrives. Thus, even if preemption may have seemed costly for the inference job at first, there are a lot of scenarios such as this where it is easy to reduce or hide the cost completely. Now, I'm just going to summarize what we've talked about briefly to close out. So in our characterization of concurrency mechanisms on GPUs, we found that without task prioritization and the ability to reassign resources dynamically, it's hard to consistently keep turnaround times low and utilization high. But fine-grained preemption is a promising solution to improve predictability and utilization, and its costs can be offset by its potential benefits. Thank you for listening, and if you'd like to find out more, you can visit our lab's website using the QR code here.